Hello again. Welcome to part 6 of chapter 16. In this video, we're going to talk about how to use the Ka-Kb table. In the last video, we talked about conjugate acid-base pairs and how we can convert from a Ka to a Kb or vice versa. And today, we're going to talk about how to read and use this Ka-Kb table. So let's get started. Okay, so here's a snapshot of one Ka-Kb table. These Ka-Kb tables are found in the appendix of your textbook. Let's get a pen going here. Found in the appendix of your textbook. I have also uploaded a PDF of this Ka-Kb table that I am using onto World Class. So look in the content section of your course for that. You will see all of these Ka-Kb tables look a little bit different, but they all contain the same sort of information. They will all contain the name of the species and the chemical formula. A lot of them will show the Lewis structure of that species and will indicate the proton or protons that are acidic or the portion of the molecule that is basic, and it will list out its Ka values. Now know that these Ka values are for a specific temperature and at a specific concentration of solution. And so it's very possible that different Ka or Kb tables will have slightly different values. But ultimately, when you are doing these problems, it doesn't matter which one you use as long as you are using the table correctly. So each of these entries on the table correspond to very specific reactions. So this acetic acid entry corresponds, it is listed as a Ka, and that means it corresponds to the acetic acid, CH3COOH, reacting with water and behaving as an acid. So that means that water is the base takes the proton and leaves us with the acetate ion and H3O+. This reaction is described by a Ka that is equal to 1.8 times 10 to the minus 5. And that is the Ka that we find in our table. So it's important to notice that the Ka in the table is trying to represent exactly this reaction. So exactly acetic acid behaving as an acid. Now likewise, there's a portion of the table devoted to bases. And so like the acids, it gives us the name of the base. It also indicates the portion of the species that is basic. In this case, it's this nitrogen. And it gives us a value for Kb. So again, this entry in the table corresponds to a very specific reaction. This entry corresponds to ammonia reacting with water and behaving as a base. So that nitrogen takes that proton, creating NH4 plus OH minus. And this reaction is described by a Kb that is equal to 1.76 times 10 to the minus 5, or exactly the value that is found in the table. So sometimes things get a little more complicated. there are molecules like this arsenic acid that have more than one acidic proton. So in the case of arsenic acid, we have 3 acidic protons. And that means that we get 3 Ka values. And in this table, this first one is Ka1, the second is Ka2, and the third is Ka3. And just like for the monoprotic species that I showed you a minute ago, each of these Ks correspond to a very specific reaction. So Ka1 corresponds to arsenic acid H3ASO4 reacting with water as an acid. So the water is the base and the water takes a proton. Now this is Ka1, and so the water is only going to take 1 proton. So I get H2ASO4 minus plus H3O plus. Now, Ka2, this reaction that is being described does not start with H3ASO4. Instead, it starts with the conjugate. So it starts with H2ASO4 minus plus water. But again, it's an acid, and so that means it is donating its proton. It's forming an equilibrium with the dianionic, the 2- version of this arsenic acid, and H3O plus. Notice how in this reaction only 1 proton was transferred. And then likewise Ka3 starts with the conjugate of the Ka2 reaction, the dibasic version, the 2- plus H2O, and it's an Ka, so this dibasic species is going to be behaving as an acid and donating a proton and forming ASO4 3- plus H3O plus. Something to notice about these reactions. Not only are these reactions balanced in terms of all of the atoms match on both sides of the arrow, but also the charges on each side match. So in Ka1, on your reactant side, we have a total charge of 0. And on the product side, our total charge is equal to 0 because +1 plus -1 is 0. If you write out one of these reactions and your charges do not match on either side of the reaction arrow, you have a problem. So you should make sure to be checking that as you are checking that these reactions are balanced. But the important part to remember here is that for each of these Kas, it is talking about transferring 1 proton at a time. Okay, so let's talk about the same thing, the same idea, but with a base. So I have ethylene diamine. I'm going to simplify this as B because it's a lot to write. But notice that I have 2 nitrogens in this molecule that both are basic. And so I have in the table Kb values for Kb1 and Kb2. So the Kb1 reaction corresponds to the base reacting with water and it's a base, so its lone pairs are going to take a proton, making BH plus OH minus. And then KB2 is this conjugate acid reacting with water to form the doubly protonated base, so HB2 2 plus OH minus. Again, notice how the charges are being balanced on both sides of the reaction. And also notice how I'm only moving one proton at a time. Okay, so from here, we're going to start moving into how we apply all of this to predicting the pH of solutions when salts are dissolved in water. And we're going to need a good understanding of this Ka-Kb table to be able to do that. So I would recommend that you open up a Ka-Kb table and you begin writing out some of these reactions corresponding to the values that are listed in that table to practice how these happen. If you have questions with that process or you want me to check your work, please schedule an appointment with me on office hours or post to the discussion board or shoot me an email. I'm here to help, and I hope this makes a little sense. Thank you.